All right, hey everyone. There are some questions about the miscellaneous topic worksheet, so I do want to spend a minute going over. This is page 4. So these have shown up on AP exams, but I would consider this kind of like a minor topic. If it shows up, then there's only going to be one of these. So and there's always going to be some random problem that shows up on the AP exam. So let me go over limit definition here. So this is based off, this is number 12 on the miscellaneous worksheet. So this is based off of Riemann sums. So Riemann sums, we know is just an approximation. If we have a curve and we have, let's say, 4 subintervals, we can create these rectangles based off of those subintervals. But we know that at best it's going to be just a decent approximation, right? It's not going to be very good. There's going to be gaps all over the place. And so the idea is, well, what if we keep increasing the number of rectangles, right? If we keep increasing the number of rectangles, then we can cover up more of the gaps, and the gaps that are still there will be significantly less. But then that kind of begs the question that, well, what if we keep increasing the number of rectangles, where we have infinite number of rectangles, and technically shouldn't that allow us to fill in all the gaps, and then we can not only get a good approximation, we can actually get the actual area. So that's the idea behind this. The idea here is we're going to push the number of rectangles out to infinity, but we have this little formula that will allow the formula to just go ahead and hit all the increments, the intervals, and then find all the heights, and we just have to just work the formula. We don't have to look at every incremental value to find the width and height. Okay, so let me just kind of show you why this formula is the way that it is. Let's say we're just going from 0 to 2, right? And I wanted 4 intervals. Then you would do b minus a over n, which is 2 minus 0 over 4. And then you would manually find the width yourself. You would say 0 plus 1/2 is 1/2, plus 1/2 is 1, plus 1/2 is 3/2. And if I asked you for the area of these rectangles, you would do all this by hand. You would say 1/2 times, let's say I asked for right rectangles, then you would say times f of 1/2. And then you would say 1/2 times f of 1. Then you would say 1/2 times f of 3/2. Plus 1/2 times f of 2. And then you would go about plugging the 1/2, the 1, into the function, get the y value, and then get the width and height. But all this is kind of manually based, right? You're doing everything by hand. So this formula kind of takes that away from us. This f of left endpoint plus width times I is going to increment and find the next value for us. We're not going to have to say, okay, 1/2, and the next one is 1, the next one is 3/2. It's going to find all those values for us. And then the f of left endpoint, it's going to take the value and insert it into the function as well. So it's kind of, in a way, it's kind of automating a lot of the process that we would do if we only had 4 subintervals. Okay, here there's infinite subintervals, but the notation here is indicating that there's a width component, there's a height component. But if we go through this formula, it will gather all this information for us. Okay. So let's look at this problem here, number 12. Which of the following limits is equal to the integral from 0 to 2 of 1 plus 3x dx? So we're going to go through this process of treating it like infinite rectangles. So we're just going to follow this formula. This formula will give us the width component, the height component, and it's going to merge all that together. So we don't even have to do as much calculations. So we're just going to follow everything that the formula says. The formula says there's the a and the b and the n value. So our a and b value are our left and right endpoints. So we'll say 2 minus 0 over n. Normally we would say 4 subintervals or 8 subintervals or 16 subintervals. We're going to leave n alone because eventually we're going to push n out to infinity, and we want to have that flexibility of increasing the number of subintervals. Okay, so that means our width is just going to be 2 over n. Okay, I'm just going to put into the formula as I see it. Width, that's my width, 2 over n, times f of left endpoint. So just understand your left endpoint is your a value, and my a value is 0. Plus width times I. So 2 over n times I. Okay. So I'm going to do a little bit of cleanup. You see how the 0 can drop out. So I'm just going to rewrite this as 2 over n times f of 2 over n I. Okay. Now the next thing is we want to get this out of function notation into my specific expression. Okay. So let's think of this as our function. Okay. My function is 1 plus 3x. I want to insert this into my function. So I think the cleanest way so that you know so you're not inserting these into the right place is rewrite the function, but leave a space where the x was. So I'm going to say f of parentheses equals 1 plus 3 parentheses. So I'm literally just removing an x, and in place of it, I'm putting a parentheses. And now I'm just going to insert the 2 over ni into the parentheses, and that will ensure that I'm not putting the 2 over ni in the wrong place. Okay, so this is my height component. This is my width component. I can do a little bit of cleanup here. This will become 6 over ni. And now I have width and the height. And that's going to match best with D. Okay, Mira, did that help?
Yes, it did. Thank you.
Okay. Okay, so really this is, I'm just going to take what you guys suggest. Are there any questions or concepts you want me to go over or review, or any problems that you are working on that you needed some support with?
Mr. Yang?
Yeah.
Could you just quickly go over one-sided limits, please?
Oh, yeah. Okay, sure. Yeah, that has not shown up in a while, has it? Okay, but that's good. All right, I'll do a couple of variations. All right, so let's say we have a one-sided limit problem, but you're going to go through your steps like you normally would, and then you're going to ignore the one-sided limit. So we're just going to enter in the 3. I get 0 over 0. So this is very specific, right? I know that the limit does exist. There just happens to be a hole in the graph. So we have two options. Either we can factor or we can go through L'Hopital's rule. But in the end, we're going to get a real number, and the one-side limit is not going to play an impact on this problem at all because the limit exists. If the limit exists, then it doesn't matter if you're coming from the left side or from the right side. They will all be in agreement. So if you choose to do L'Hopital's rule, it'll be 1 over 2x because the 3 and 9 goes away. And then you will enter 3 in for x. You'll get 1/6. Okay, so if there's a hole in the graph, your one-side limit is not going to play role at all. Okay, now let's look at this. Okay, so now we're going to go through our same process. We're going to evaluate the limit. We'll get 3 over 3 minus 3. And now this is telling us something different. Okay. So both of these are discontinuities, but this one is one where there's a hole in the graph, but the limit still exists. This is a jump discontinuity. This means that there is a vertical asymptote. The limit does not exist. But we can't just say limit doesn't exist, because now we go back to our problem and we realize, oh, it's not asking about the full limit. It's only asking about the behavior from the left side of 3. So that means we know there's a vertical asymptote at 3 because of this scenario. But this problem is more concerned with what's happening with the asymptote. Is it going up or is it going down? Right? We just don't know which variation. And this will, if this is going to show up, it's going to show up on the non-calculator portion. So if we're at this scenario where we realize limit doesn't exist, but it's asking about a specific behavior, and we're choosing between one of these directions that the branches are headed towards, then we have to rely on decimals. So we choose a value that is relatively close to the direction that we're headed from, which is 2.9. And when we plug into our expression, we just want to know, is this overall value going to be positive or negative? If it's positive, we know it's going to be headed in that direction. If it's negative, we know it's going to be headed in this direction. So 2.9 divided by 2.9 minus 3. I don't really care about the value. I just want to know what the sign is. Numerator is positive, denominator is negative. So negative tells me it must be looking like this. Okay, did that help?
Yes, thank you. I appreciate it.
Okay.
Mr. Yang, could you
Yeah.
go over synthetic division equation?
Yeah, that's a good one. had one on my on the miscellaneous worksheet here. Actually, I think while we're on this topic, I want to just go through problems that look very similar, but they have significantly different applications or approaches. I think that could be helpful. Let me see if I can find that. I just thought of it. Oh yeah, this is good. All right, so I'm going to put this in the chat box and see if this is. Okay, let me print this out. Okay, so you guys see this in the chat box. I think I sent it to you. Let me go through the scenarios of problems of integral problems that kind of look similar, but they have very distinct applications. So the first is if you see an integral and there's only one term in the denominator, like this, you want to try to split up into individual terms and then just approach it from a power rule perspective. Okay. So no use substitution. If there's only one term, you want to split it up into individual terms. So just a quick instance of that. If I were to split up into individual terms, I can clean this up, bring up the numerator, and then once I have it cleaned up, I can approach them individually. So 1/2 is power rule, 1/x is natural log, and then x to the -4 is power rule. But our first approach is trying to just separate into individual terms. Expansion, power rule is going to be our first option. That also kind of applies with E. If I only one term involving E, I also want to spend the time to separate into individual terms, because once it's separated, then I can treat each like an individual problem rather than one extended problem. Okay, so if you only see one term in the denominator for integrals, see if you can try to break them apart and then divide and conquer. All right, so that's if there's only one term in the denominator. Right. Second scenario, if there are multiple terms in the denominator, but the denominator has a degree that is 1 higher than the numerator, that's an indication that most likely use substitution is going to be the best fit, because the degree in the denominator is going to handle the degree in the numerator relatively easily going through your substitution. So if my u value is 7x squared minus 4, look at how the derivative produces 14x, and that 14x is going to match up nicely with that 5x. And once that cancels out, I'm left with an expression that is perfectly set up for either natural log or whatever rule that I need to use. All right, so if my degree in my denominator is 1 higher than my numerator, that's a good sign that I'm dealing with u substitution. Right. Okay, next scenario is where you have multiple terms, numerator and denominator, but the numerator is either the same degree as the denominator or it is higher than the numerator, than the denominator. Okay, if it's the same degree or if it's higher, then we rely on synthetic or long division. I think it's pretty rare that you see long division. I just haven't seen any recent tests with long division. I feel like synthetic division is going to be the better bet. So let's do 2 examples of synthetic division. I'll do one where the degrees match, and I'll do one where the degree is higher by 1, but the denominator is still just a degree 1. So I see that my degree is the same. This is going to be a good fit for potentially synthetic division. So synthetic division, I'm going to be taking the factor from the denominator. So I'm always choosing the opposite sign. And I'll create a half box. And I'll list out the coefficient here. So 4 for the x to the first power, the -3 is for the constant. And we're just going to go down the list here. We always bring down the number below the line. We multiply.
Mr. Yang,
Yes.
how did you get the 5?
Oh, how'd I get this 5? Because I always set x minus 5 equal to 0. So to get to this number
thank
here,
you.
yeah, we always set this equal to 0. You get x equals 5. Yeah, so basically it's always going to be the opposite of what you see in your expression. Okay, so 4 comes down, we multiply, and we add, and then we stop, because this is 4x, right? So we know that every term that comes down is going to have to be 1 degree lower. This is already a constant, which is telling us this must be the remainder. Oops, -5. Now, synthetic or long division does not solve the problem, but what it does do is it creates a scenario where it's easier for us to find the integral. And now we have a much easier time because this one, we can use power rule. And this one we can use u substitution, natural log. So 4 becomes 4x, u substitution. Or if you already recognize this is natural log, then great, you can save a few steps. Natural log of u, replace the u back in terms of x, plus c. From my worksheet, this is number 10 off of the miscellaneous worksheet. Let's do this one here. So if you look, you see how this is a perfect scenario for synthetic division. Degree to the first power, and the numerator has a higher degree than the denominator. Right? There's more than one term, so I can't just split up into individual fractions. And this is not good for U substitution. So we're going to try synthetic here. Always take the opposite sign of what you see here. And we're just going to put down the coefficients down in front. 1 for the x squared, -1 for the x, and -5 as the constant. Drop the number down below. Multiply. Add. Multiply. Add. We start off with x squared, so all of our degrees will fall by 1. Degree 1, constant, remainder. Okay, we haven't solved the problem, but we have made it easier for us to do our integral here. We have 3 terms: power rule, U substitution, natural log. Now we can work in the bounds. Upper bound first. Minus, big parentheses. Oh, I messed up. This is 4, right? Not 3. So this is 2 minus 6 plus natural log of 4 minus 1/2 plus 3 minus natural log of 3. Combine these like terms. 2 minus 6 is -4. -4 plus 2.5. Is 8 plus. So that's -3/2. Now the answer choice is cleaning this up a bit more. We're going to use quotient property here. Answer choice A. Okay, so that's synthetic division. And then finally, there's also a scenario of integral problems where the degree is higher than the numerator by 2 or more. You see how this is different from U substitution? U substitution is degree that is 1 higher. But when you come to a cross scenario where the degree is in the denominator is 2, the degree is more than 2 or more, so x squared versus x to the 0 power, x to the 4th versus x to the 1st power. So your denominator has variable exponent that is higher than the numerator by 2 or more degrees. Then we got to involve potentially arc trig. Okay, and arc trig are ones that we may have to go through potentially complete the square. So why don't we do these as well? Okay, so this is not expansion. This is not U substitution. This is not long division, not synthetic division. That difference is kind of forcing us into arc-trig territory. But we don't see any radical, right? So basically the only rule that this can fall under is arctangent. So we're going to target arctangent. So in order for us to pick out the a squared and u squared, we got to have this to be in the cleaner form. So to do that, we're going to complete the square. So to complete the square, we're going to give that third term a space because we're going to fill in that space with a value that will allow this to factor and allow this to clean up. And what goes in the space is b over 2 squared. Our b value is this -8. -8 divided by 2 is -4. And it doesn't matter if it's negative or positive because it's always going to end up being positive. Oh, you know what? This did not work out the way I was supposed to do this. Because these, I should not be left with a negative here. Okay, let me change this a bit here. Let me make this 24. Yeah, this is not going to work out for arctangent. But I'm going to make a slight change. Our process will still stay the same, just so that it'll come out where it will actually work. There, that's better. Okay, so we have a plus and a minus because we need to ensure that whatever number we add, we subtract it because we don't want to change the overall value of the expression. So now we're going to factor. Multiplies to be 16, adds it to be -8. It's going to be x minus 4 and x minus 4, so x minus 4 squared. Combine the remaining term here, and we get 8. Okay, our denominator is coming together a little bit more nicely. Now the a is going to represent the constant, the u is going to be the variable, so these could be flipped around, it's okay. But it looks like this is going to be our u value, and our a value is still not ready for us to find, but if we can get a parentheses and squared set up, so I'm going to force the 8 into the parentheses without changing the overall value, so that's going to have to be square root of 8. Okay, so our a value is root 8. Our u value is x minus 4. If we go through u substitution, we're not going to get any coefficients that we got to keep track of, so we can jump directly into our rule here. My a value is root 8. Our tangent of u over a. Let's see. It's okay to have radicals in the denominator. That's perfectly fine. Okay, so while I'm at this, why don't I also do the other arc trig problem, which is this one here. Okay, so this one is also arc trig, because if you look at that difference in degree, 4 versus 1, that is definitely more than 2. We know that we're in arc trig territory. We see the square root, we see the constant coming first, followed by the variable. This is going to be the best fit for arc sine. Arc sine is the only one without the 1 over a in front. So it looks like we don't have to complete the square. We only have 2 terms, so as long as we can get parentheses squared to show up, we can isolate and find our a and u value. So I want to force these expressions into the parentheses so that I can clearly identify my a and u value. So the first one is pretty obvious. 1 is still 1 squared, so nothing changes here. But x to the 4th, I got to force it as x squared in here. And now I can pinpoint my a and u value. A is 1, u is x squared. And I can find the derivative here. Make my substitutions. The 5x stays. A squared minus u squared, and then du over 2x. X's cancel out. I have a perfect match. I'm just going to follow the rule. The 5/2 is going to end up being as part of my answer. My u and a value, x squared over 1. Okay. What else do you want to see?
Could we look at how Riemann sums are like in over approximations or under approximations on a certain graph?
Sure.
Like how that varies?
Okay. All right, so order the approximations from smallest to largest. Okay, so I have a decreasing function that is concave down, and this represents the exact area. Okay, so we'll go from smallest to largest. I think the smallest is going to have to be the right Riemann sum. Okay, so this is what right Riemann sum looks like. So right Riemann sum is the one that is going to produce an under approximation, but there's going to be a significant gap here, right? So this is going to be the smallest. I think the next one is going to be trapezoid. Because of the way that the graph is shaped, all of our trapezoids are going to sit kind of inscribed. It's going to be inside the graph. All right, it's tough to draw it because trapezoid is, it does such a good job. Like I can barely tell that that there's, yeah, but you can tell that it's definitely going to be under, right? So this is going to be trapezoid. Followed by the exact area. And I think the largest is going to be the left Riemann sum. Because we have, this is the, I think this is the only one that's going to produce an over approximation. Everything else is either exactly the same or a little bit under. So right, trapezoid, area, and then left. But you know, there's none of these you want to memorize. You want to just sketch the graph and then convince yourself what the approximation is in relation to the exact area. Okay, does that help a little bit?
Yes, it does. Thank you.
Mm-hmm.
Mr. Yang,
Mm-hmm.
would we be able to do a log differentiation problem?
Yeah. Yeah, this one is from Miscellaneous Worksheet number 7. And I guess while I'm doing log differentiation, I want to show the variations of them that in terms of how it looks like certain derivative rules, but they're very different. Let me show the distinction between yeah, okay, let's just do these here. Okay, let's say we have y is equal to x squared versus y is equal to 2 to the x versus y is equal to x to the 2x. Okay, you see how these all kind of look similar? They all involve 2's and x's, but these all involve base and exponent. But depending on where the variable is and where the constant is, it's going to significantly alter how we approach each problem. So if I have a variable raised to a constant, this is power rule. So y prime is just equal to 2x. Easy enough. If I have a base raised to an exponent variable, this is going to be an exponential function. And we have a rule for this, right? The derivative for a to the u is natural log of a times a to the u times u prime. So natural log of 2 times the original function times the exponent's derivative. Looks kind of similar, but very different rules. Now, last scenario, x to the 2x. We don't have a rule for a variable raised to a variable. So our workaround is log differentiation. We don't have a rule that can handle a variable raised to a variable, but what if we introduce natural logs into this expression? Then we can bring that exponent down, and once that exponent comes down, we have a lot more options available to us in terms of derivative rules. Okay. So here are the steps that we're going to do. Number 1, take the natural log of both sides. Number 2, use log properties. Typically, we use power property. Bring that exponent down. Third step, there's going to be implicit going on the left. And then there's going to be product rule on the right side. And then we got to solve for x. Okay, so sorry, we got to solve for dy dx. All right, so I'm going to give myself plenty of space here to handle this problem. Okay, so we realize this is not power rule, this is not exponential, this is variable raised to a variable. So take the natural log of both sides. We know this is log differentiation. So once we are in a log expression, that 2x is now free to move. So that 2x can come down in front. So I have natural log of y equals 2x times natural log of x. Okay, I want to find the derivative, but the derivative of this side is natural log of u is u prime over u, so it's going to be 1 over y, but we just took y's derivative. Y is no longer by itself. We got to attach that dy dx. And the right side, we got to handle using product rule. Bring the y over to the right side. Our goal is to isolate dy dx. (2x over x), I can get the x's canceled out, so just plus 2. And then final step, let's replace the y back in terms of the original equation. Okay, does that help? Seeing the similarities, but then also distinct differences and the specific steps for log differentiation.
Yes, thank you.
Good. Picture.
Mr. Yang,
Yes.
how common do you think like the miscellaneous topics are going to be on the exam? Do you have any idea of that?
I think that's a good question. I mean, a lot of these problems were picked from previous years. So yeah, I'll go through just kind of my general thoughts. I think this is pretty common, having to find the second derivative function and then having to involve implicit along the way. So I think this is something that is good to know. I've seen it on FRQs. I think we've seen it under FRQ, I think today for 2019. So, so I think this is good to know. Are you guys okay with this? These types of problems? With absolute value functions, I think the tendency is we see an absolute value function and we just don't know what to do with them. So what my suggestion is, if you see an absolute value function, just write it as a piecewise function. Even if it looks really messy, just start with the basics, right? You know that the absolute value of x is just a piecewise function that you can split up into a positive and a negative version. And if I can get a portion that I can recognize into a piecewise function, then I can always adapt it by adding to it. So if the absolute value of x is this piecewise function, then the absolute value of x divided by x is just dividing all these terms out and getting it into something that is a lot more reasonable that I can actually graph, because that's just y equals 1 and y equals -1. Right. So if you ever see an absolute value function, just think, all right, I'm going to start with the basics. I'm going to ignore all the messiness around it. I'm just going to create kind of my parent expression, and I'm just going to add to it depending on what else is needed. And a lot of times that messiness will clean up into something that is actually, fairly easy to work with. So yeah, I think it's good to know. But, if it shows up, it'll only be one question. And, there's no, like this, maybe this has shown up like once in the past, like 5 years. So, it's shown up before, these are actual AP problems. But the likelihood of them showing up, it's kind of like, yeah, it's just rolling the dice. We just so that's why I focused my attention on the main topics. But I figured, well, if you want to spend time on these smaller topics, these could show up. Limit definition. I know it's a minor topic as well. Log expansion. I guess this is minor, but I think this is good to know because when you see a log problem, maybe your natural instinct is, I want to do u prime over u. But whenever you see a log problem, just think, wait, maybe I can expand first, right? And that can allow your process to be a lot cleaner if you look to expand first. So here, I would rather expand first, make it natural log of the numerator minus natural log of the denominator. And if I keep expanding by bringing the exponent down, now my problem gets a lot easier because now I can just handle these separately as u prime over u rather than a messy quotient chain business here. L'Hopital's rule, you guys have seen it, but here I just want to point something out here. If you see a L'Hopital's rule that is in this format, understand that here, look at how this is set up here. It says h approaching 0. That means your h is your variable, and everything else is a constant. So if I want to go through L'Hopital's rule, well, this is first off a limit problem, right? So let's look at this one here. If I evaluate the limit here, h is the variable. I replace h with 0. I get tangent of 3x minus tangent of 3x over 0, which is 0 over 0. So this is perfectly set up for L'Hopital's rule. But remember, h is the variable, so we're going to take the derivative of tangent of 3x plus h with respect to h. So that means the tangent of 3x plus h is going to be secant squared of u times u prime. Okay. And let's see, another way of writing this is tangent of 3x plus 3h. Right. And the derivative of tangent of u is going to be secant squared of u times u prime. And the u prime is going to be 3 from the h, not from the 3x. The x is a constant, so that's going to go away. And then the tangent of 3x derivative is going to be 0 because this x is not a variable. So this is the constant. So that drops out to be 0. And then h becomes 1. And then once we're here, we can reevaluate the limit, hoping that we can get it out of 0 over 0 territory. 0 and for x, sorry, 0 and for h, we get 3x. So bring the 3 out in front. 3 secant squared of 3x over 1, which is 3 secant squared 3x. So just be careful. Sometimes you have limit problems where x is not the variable, it's h. If it's h, just remember that anything else that you see is a constant. If there's no h involved, then it's a constant. So same thing here, that's a constant. Treat x as a constant because h is a variable. Matching slope fields, this is good to know. I would say this is a pretty strong chance of showing up. So look for slope 0, slope undefined, slope positive, slope negative. If you can gather some information, you should be able to use that to help you eliminate the wrong choices. Because if it's a true correct choice, then any order pair that I see, I should be able to plug that order pair directly into the derivative and get that slope, whether it's positive, negative, 0, or undefined, depending on what the derivative is telling it should create. 22, 23, these are just kind of variations of differential equation. So these problems, I guess they've shown up in the past couple of years where you're trying to match the solution. So you find y prime, you find y double prime, and it's kind of tedious, but you're just trying to see this puzzle where can I get my y prime and y double prime to fit in the equation so that it'll match my original problem. So for instance, number 22 here, y equals e to the 3x minus 5x plus 7 is a solution to which of the following differential equations. So if I look at my answer choices, they all involve y double prime and y prime. So I'm going to find those derivative equations. So y prime is e to the 3x times 3 minus 5. 7 goes away. Y double prime, I keep going. 3e to the 3x times 3 minus 0. So I'm playing with 3e to the 3x and 9e to the 3x, and I'm going to insert these into these equations and see if it will actually give me 0. So I'm playing with these y prime, y double prime, and see which one will make it a true statement. And it just so happens that it'll work for A. Because if I insert 3e to the 3x minus 5 into y double, if I insert 9e to the 3x for y double prime, and 3e to the 3x into y prime, I'm able to get everything resolved. Everything cancels out. So that's the approach for these verifying differential equations. More of the same, 25, 26. Trig related rates. Doesn't show up too often, but it's good to know. You know you're starting with a trig equation, either sine, cosine, or tangent. And you know you're not just replacing theta, you're replacing the entire trig ratio or trig function with the ratio. Right, so I think we did this fairly recently, but it's good for you guys to review if you're. Yeah, this is, I don't know, this is a lot. This is an area problem where we're trying to find a vertical line that will split something in half. I don't know, maybe it's not worth going through all this trouble to go through it. Yeah, I don't think this will. Well, maybe I'll go over it. Let me just hit some of these other things here. Expansion, and then last page here, absolute value. If you're asked to find the absolute value of a integral of absolute value function, this will have to be a part of a non-calculator. So what you do is you sketch the graph out absolute value of x minus 3, and then you're going to see two triangles form. And then from the two triangles, you'll be able to identify the height and the width of this triangles, and then do 1/2 base times height, 1/2 base times height. Okay, so yeah, maybe I'll just go through and explain through this concept, and it's not too bad, I guess, but it is a little bit tedious. It's a good chance to kind of review area and volume as well. So let's say we have y equals square root of x. Find the area of the region. So area is just top minus bottom. Top is root x, bottom is 0. We're going from 0 to 4. We go through power rule, plug in upper and lower bound, and we get 16 over 3. Okay, so we know that this full area is 16 over 3. All right. And then part B says, find the value of h such that the vertical line x equals h divides the region into two regions of equal area. So if I were to drop a vertical line, it's not going to be right directly in the middle, right? Because this curved region is going to be a lot more area in a smaller space than over here. So I'm going to put it closer to the right side, but I'm just going to create a scenario where I'm going to say this side is 8/3 and this side is 8/3. Right? So basically, I'm trying to find that vertical line that will allow me to split this region into regions with the same area. And if that's the case, if I know that this is 16 over 3, then I want one region to be 8/3 and I want the other region to be 8/3. So we're basically trying to figure out where is that vertical line that will allow this region to be 8/3. So what I'm going to do is I'm going to cover up this region. I'm just going to solve this problem. I'm going to solve this problem. The integral of top minus bottom from 0 to h is equal to 8/3. And I'm going to work backwards. I'm work backwards and figure out what is the upper bound that will cause this area to be 8/3. So that's exactly how I'm going to set it up. From left to right, 0 to h, top minus bottom, root x minus 0 is equal to 8/3. So the interesting thing is that this cannot be entered into the calculator. We got to do this by hand, okay? Because the calculator can't handle a bound that is a variable value. So we're just going to go through our process. Root x is x to the 1/2. If we go through power rule, it becomes x to the 3/2 over 3/2. We plug in our upper and lower bound. Upper bound, h, becomes 2/3 h to the 3/2 minus 2/3 h to the 0. But now we have an equation, 2/3 h to the 3/2 minus 0 equals 8/3. We already know what the area is, so we're just working backwards to figure out what the upper bound limit is. So now that we're down to 2/3 h to the 3/2 equals 8/3, I'm going to divide by 2/3, which is the same thing as multiplying by 3/2. Clean up, solve for h. H to the 3/2, so I'm going to raise 4 to the 2/3, raise both sides to the reciprocal, and 4 to the 2/3, you can leave it like this, or you can rewrite it as cube root of 16. Okay, so that's the basic concept there.
All right, thank you. I appreciate it a lot.
Mm-hmm. All right, so some of you have sent in some problems So I'm going to try to work on them, but it may not be until late. So what I'm going to do is under this help session link on my website, any questions that come in and I'm able to solve it in time, I'll take photos of them and I'll just insert it into miscellaneous questions answered. And if you want to take a look at them to see what other students were asking about that I have time to solve, I'll go ahead and put that up. But yeah, thanks for being here. Last stretch here. Hopefully you guys do. Hopefully I feel comfortable going to the exam tomorrow. And yeah, wish you best of luck.
Thank you. Have a good night, Mr. Yang.
All right, have a good night. Thanks, everyone.
Thank you.
Thank you. Have a good one.
Thank you. Bye.
Mr. Yang.
Hey, bye.